Welcome back, compadres. Today we're talking reservoir engineering and the pressure buildup test. To run a pressure buildup test, operators will run the well at a constant rate for an extended period of time, and then they will shut it in. Then they record the bottom hole pressure change with time, and from this data, you can get reservoir characteristics like permeability and skin, much like you can the drawdown. But an added benefit of running a pressure buildup test is you can get average reservoir pressure. And if you're a reservoir engineer, that's important because we crave pressures. So guys, we're going to work through an applied example in Excel using actual gas data and show you how to get this information from a buildup test. So guys, let's get started.
Today we're going to look at pressure buildup test data to obtain reservoir characterization parameters for a gas well. So this shows you a plot of a pressure buildup test. You have pseudopressure on your y-axis because we're looking at gases, and you have this quantity defined as Horner time on the x-axis, and we're going to cover that in the upcoming slides. But essentially it's the same concept as a drawdown. You fit a straight line to your straight line portion, and from this straight line you can get reservoir characterization parameters. Before we jump into it, I want you just to think of the key concepts. This pressure buildup test that we're doing this analysis today is for radial flow. In addition, this concept known as superposition is applied to get us Horner time, and we're not going to really cover it today because it'd take a little bit more time to cover this topic, but just realize from superposition we can get a equation that basically simulates this buildup test. And so Horner time is a direct result of superposition, and also we have noise in our data in the form of wellbore storage. And if you don't know what a pressure buildup test is, it's where you shut in the well and you record the pressure change with time at the well flowing or at the bottom hole condition. So it's the opposite of a drawdown, where in a drawdown you just open up the choke, in a pressure buildup you close the choke. And then from this buildup test we're going to go through today, we're going to be able to show you how to get permeability, skin, and average reservoir pressure. You can also get original gas in place if you have another pressure using material balance, but we're going to cover that later. Before we get into it, I kind of want to discuss the theory. Before you get into the equations, just realize there's some key information you need to obtain from this plot. Number one, you can get your average reservoir pressure at a Horner time represented by the log of 1, which represents infinite time. We're going to show you in the equation, but you can get your reservoir pressure, average reservoir pressure, which is represented by the y-intercept on a semi-log plot. Further, you need to be able to get this pseudo pressure at the well flowing condition after 1 hour, so it's on this straight line portion. This goes into our skin equation. So essentially what this quantity is when you shut in the well, you're going to get the bottom hole flowing pressure at 1 hour after you shut in the well from this straight line. Further, you need to know your time produced. So essentially you produce the well, and then your time produced is when you shut in the well. So you produce at a constant rate, and then you shut in the well, that's your time produced. And then from this line you can get permeability, which represents the slope. So if I'm going to save you some grief, you can derive this line using superposition, and from that equation you can get permeability and you can get skin. So for skin, you need the well flowing condition after 1 hour after you shut it in off this line, and then you subtract the initial well flowing pressure at time 0. And in addition, from superposition you can derive the Horner time equation. So the Horner time equation is essentially your time produced plus your shut-in time over your shut-in time. And if you take a look at this equation, if shut-in time approaches infinite time, then your Horner time equals 1. So that represents infinite shut-in time. At infinite shut-in time, everything should equalize in the reservoir. Theoretically, everything should equalize in the reservoir, and you should be able to get your average reservoir pressure at your bottom hole condition. And so that's why this y-intercept is important, because from this solution right here, we're assuming at infinite shut-in time we can get average reservoir pressure. And so this shows you the actual data we're going to look at today. But here's your skin equation, your permeability equation. You get your perm from your slope, and then you would calculate your skin. Same as a drawdown. And more importantly, you have some noise here represented by wellbore storage, and here's your straight line portion. And then this point represents your well flowing condition at 1 hour on this line after you shut it in. So you have your time produced, you shut it in, you add an hour, and that's your pseudo pressure at a well flowing time of 1 hour, and this is your average reservoir pressure. So these show you the steps we're going to go through today in the Excel analysis. You can pause the video and read through this, but this is essentially what we're doing. And the references I used is Gas Reservoir Engineering, written by Wattenberger. So that's the reference we're going to reference today. That's where the data came from. So if you don't understand what I talked about, don't worry about it. We're going to go through the application in Excel. So let's get started. So here's our spreadsheet. So what I've done is the first thing you're going to need to do to run a pressure buildup analysis is to pull in your data. So you need to pull in your shut-in time and then your associated pressures at that shut-in time, and then also your time produced. So if you don't know, I'm using this data from Gas Reservoir Engineering, written by Wattenberger, table 6.9, and we're going to kind of work through example 6.4. We're going to try to see if we can get this pressure, which is going to be our y-intercept. So this is the initial pressure from that data. As you can see, the data gives us the well flowing condition, but it doesn't give us the initial pressure. And also we're going to estimate permeability in skin. Here they get permeability of 0.029 millidarcies and a skin of negative 0.292. We're going to see if our analysis gets close to that. So I pulled in the data. Now you want to plot your data on a pressure buildup plot. And so I have Horner time on the x-axis, and I have pseudo pressure on the y-axis. And so I wrote VBA functions for this. So I got Horner time, and I'll post the code. It's just simple one-liners. It takes your time produced, and you're going to want to freeze that, and it takes your shut-in time. And you're going to want to just carry that all the way through. So the first value isn't going to be calculated because we're dividing by 0. But we can calculate our pseudo pressure now. Our pseudo pressure, I wrote a VBA function for that. It's called pseudo pressure. And it's going to take arguments, and I'm going to move this out of the way so we can get our data equals pseudo pressure. It's going to take our reservoir temperature in degrees Fahrenheit. It's going to take pressure. Our pressure is going to be in our pressure column, and you want to freeze the temperature. It's going to take gas gravity, which is, these parameters are coming from the book, 0, 0, and we have no impurities. And so we carry this down. We have our data on the plot, and it looks like I forgot to freeze something here. We want to freeze our specific gravity. And there's the data on our plot. The data was this graph was pre-formatted to take this data. So there's our data. The next thing we want to do is we want to put our straight line on this plot. So what I'm going to do is calculate a slope for the line. So we're looking to put, so calculate our slope for a straight line equals slope. Start at row 30. Freeze those, and then take the log of our x's. So we got our slope. Now we're going to use the intercept functions to do the same thing, and you want to freeze these up here. So carry it down, change this to intercept. This will be our average reservoir pressure on our line. And so that's our slope and intercept. Now we need to put our line on this plot by plotting some points. So I chose 3 points here. In this case, we're going to plot our average reservoir pressure, which represents a horizontal time of 1 hour. And here, this is going to be our well flowing at 1 hour after shut-in on our straight line, which we need to calculate skin. So I'm going to take our time produced and add 1 hour. And then I just chose a random point out in space that would essentially be plotted on this graph. So we got 3 points. So now I'm going to write the equation of our straight line, which is going to be our intercept plus our slope times the log of our times. And you want to freeze the intercept and slope. Carry that down. Okay, so this is our straight line. You can see our straight lines now on our plot. The plot was pre-formatted to take those data points. And so we have our plot now. Now what we want to do is we want to try to fit to the straight line portion. So it looks like we're taking in to account some wellbore storage. We're regressing on some of those points. So I'm going to look at this point. Let's do 106.8 as our X. So 106.8. So we're going to stop. We're going to regress off of those points beyond 106.8 or to the left of 106.8. So what I'm going to do is go up here, carry this down to 106.8, carry this down with it, and then I'm going to carry this down because our intercept takes the same points, and change this back to intercept. And so looky there, that's our straight line portion. The next thing I want to do is go ahead and look at getting reservoir characterization parameters. And so right here I can get permeability from this equation. And so we're using the same equation we did with the drawdown. So I'm going to do permeability radial drawdown. It's going to take our rate, and this was pulled in from the book, our temperature in degrees Fahrenheit, our slope off of our line, and our reservoir thickness. And screwed up there. Slope and then reservoir or pay zone thickness, my bad, it should be pay zone thickness. And so that's our permeability, 0.0307. Okay, so next we can calculate our skin, but before I calculate skin, I have some parameters here that are actually a function of reservoir pressure. So what I'm going to do is I'm going to calculate a reservoir pressure or average reservoir pressure first, and then calculate these fluid properties using correlations, because in essence you're not always going to have all your PVT data. You can easily estimate those with correlations. So the average reservoir pressure is represented by our slope, and so this is it's represented by our intercept. So this is our intercept, but it's in, because we have pseudo pressure on our y-axis, it's going to actually be in terms of pseudo pressure, which we don't want. We want it in psi. And so in order to do that, you got to convert the pseudo pressure to a actual pressure, and you have to do it numerically. So I wrote a VBA function for that, and it uses the false position method to do it, a numerical method. So it's basically a root finding method where you straddle the points and it iterates until a criteria is met. In this case, it's going to run until it gets our average reservoir pressure. So you're going to need an upper bound and a lower bound to do the false position method, and I'll go ahead and show you the code. It's called pseudo to pressure, and it converts our pseudo pressure to a pressure using the false position method, as I stated earlier. I'm not going to go into too much details, but the arguments are you're going to be your pseudo pressure, and then a lower bound pressure in psi, an upper bound pressure in psi, temperature in degrees Fahrenheit, gas specific gravity, and impurities. And it takes two pressures, and it takes your pseudo pressure, and it runs your false position method, and it runs until a criteria is met, and then it stops and it returns your pseudo pressure, or your root in this case. And we'll probably cover this in another video, but I wanted to show you this just in case you guys wanted to write down the code. You can pause the video and go through it. I highly suggest that. But that's what it's doing. So it's pseudo to pressure using the false position method. So I need two bounds. My lower bound I'm going to use as my well flowing at 0 time, because we know that will not be greater than our initial our reservoir pressure, average reservoir pressure. And then an upper bound, I'm just going to say 15,000. That's a good guess. If it doesn't find a solution, then I know that I need to put in a higher value here. But let's go ahead and calculate that with the function pseudo to pressure, and the arguments are going to be, it's going to take some of these arguments hidden behind the box. So move that first. The arguments are going to be your pseudo pressure that you want to convert to an actual pressure, which is going to be our intercept. It's going to take our lower bound, which is our well flowing condition, our upper bound, which is a guess that seems reasonable, and then a temperature, gas specific gravity, and then any impurities, and then bang. So we got a average reservoir pressure of 9,004. And so now what I want to do is I want to use this average reservoir pressure to calculate, or use our correlations to calculate fluid properties. So the VBA function I'm using is going to be UG, which calculates our gas viscosity. So it's going to take our average reservoir pressure, temperature, gas gravity, and impurities. In this case it's 0. So that's our gas viscosity, and then gas compressibility. We can also estimate that with correlations. And I've done this before, so you can go back to a previous video and look at how I use this. And so this is going to take our average reservoir pressure, temperature, gas gravity, and impurities, which is 0. So bang. And then we have total system compressibility. The VBA function is total compressibility. It's going to take our oil saturation, which is going to be 0 because this is dry gas. Oil compressibility of 0. Gas saturation. Have those values right there. Gas compressibility, we just calculated that. Water saturation. Water compressibility. And then formation compressibility. And so bang. So now that we have the fluid properties and formation properties that we need, we can estimate skin. And so this is the equation we're using. It's the same as the equation in the slides. So I'm going to go ahead and use the VBA function equals skin buildup. And it's going to take our pseudo pressure at 1 hour, which is going to be, just to refresh you, it's going to be on our straight line plot. So it's an hour after we shut in the well. So it takes our time produced at an hour. That's Horner time of 2001. And so we showed that here. We did that earlier. And so skin, buildup. So it takes that pseudo pressure at 1 hour, and then our initial well flowing pressure, which is coming from our data. So we calculated that. So this is at time 0 coming from our data. So that other point came from our line. This is coming from our data. And then it's going to take permeability. Well, shoot. I screwed up there. So I just forgot to change the box. So our permeability is going to be this value, which we calculated, the slope on our straight line, porosity, viscosity, gas viscosity, that is, total formation compressibility, we estimated that, and the wellbore radius. And so bang, that's our skin. So this is our plot. These are the values we obtained from the plot. We got permeability from the slope of 0.03007, a skin of -0.35, and an average reservoir pressure of 9,004 regressing off of these points. So you can regress off of really any of these points. You can change what you regress off of, but let's go compare the results to the book. From the book, the initial pressure or average reservoir pressure was 9,000 psi. We got 9,004. Now let's compare permeability and skin. For perm, they got a permeability of 0.029. We got a perm of 0.0307. That's pretty dang close. And then for skin, they got -0.292. We got -0.35. So that is really close. So you can see we validated this approach from the book. So our model has been validated, and that is pretty cool because we can extend this to other wells. So if we go get data from another well, we know with confidence that we can apply this and get accurate results. And so guys, that's it. So we got permeability, skin, and average reservoir pressure from a buildup test, and that's what I wanted to show today. And there's more good stuff to come. We'll probably deviate from the reservoir engineering theme a little bit, but it'll stay petroleum engineering for right now. And I hope you guys like the video, and I hope to see you again next time. So adios.